Hi. So in today's lecture, we are going to talk about doubly linked lists. So recall that in the lectures last week, we studied specific implementations of different abstract data types. Specifically, we looked at the data type linked list. And what we did was we described the abstract data type and then identified the appropriate methods, the appropriate data, and we went ahead and implemented it. After implementing the different methods associated with the abstract data type, we used these methods in a specific programming exercise. Let me recall the programming exercise for you. The programming exercise was to take two large integers as input and two large positive integers as input, and then add those two large integers. While this exercise looks to be very simplistic, it is a very interesting exercise. It's an exercise in learning how to manage and maintain linked lists, and you can add arbitrarily large integers. We made some simplifying assumptions. We assumed that the integers are always positive and that there are no decimal points and so on and so forth. Right? And most importantly, while implementing the linked list abstract data type, we also paid significant attention to programming practice. We saw how to use a C programming language to partition a large program with different kinds of data and different kinds of functions into appropriate pieces of code. I mean, each piece of code sat in a separate file. One was referred to as a source, the other was an object file, and the third one was a header file. And all these are important programming practices. And in today's lecture, we are going to extend the linked list data type to define the doubly linked list data type. And when we define the doubly linked list data type, when we implement the doubly linked list data type, we are going to reuse code. Right? And reusing code, already developed programs, is a standard approach to designing systems. What you do is you take a piece of code that is tested and that is deployed, and you want to identify some minor functionalities that you want to add or change, and you modify the code to incorporate this minor addition or the minor change. Right? Today what we will do is we will take this linked list implementation that we have and implement the doubly linked list data type. And during this implementation, you will see that one has to be extremely careful when one reuses code. While this is not the central theme in the lecture, it is a very important associated theme with programming. Right? So now let's go to the slides for the doubly linked list data type. And in these slides, you will notice that there is a strong motivation for the doubly linked list data type. Right? In other words, we are interested in the issues of efficiency associated with this big int arithmetic, the big integer arithmetic. And to deal with these efficiency issues, we essentially introduce this doubly linked list data type. And that is the focus of today's lecture. So let's go to the slides. All right, so doubly linked list. So as I said before, we are going to extend the list abstract data type. And this is a summary of the list abstract data type. Recall that the data is organized in a list-like fashion. And we have some generic methods to query the list itself, whether it is empty or how many elements are there in the list. We can also query a certain position to find out whether it is the first or the last position. And then we have access methods which will return pointers to specific positions in the list. And finally, we have update methods which change the data values at different positions in the list. Let's look at the qualitative effort in maintaining a linked list. I use the word qualitative because I'm not going to specifically talk about the efforts in terms of quantities like time. right? So normally efficiency is quantified in terms of time, and or rather time is one of the ways of quantifying efficiency. And on the other hand, this discussion is about the qualitative effort in maintaining a linked list. Right? So let us just look at a simple exercise that we repeatedly performed while adding a large number. Recall that the addition was from the rightmost digit, otherwise the least significant digit, and we moved moved towards the left repeatedly, adding the individual digits, keeping track of a carry that gets generated. Right? Also, let us recall that in the list implementation, the number was visualized from the left to right fashion, whereas the addition is from the right to left fashion. Consequently, a repeated task that we performed was to find a position which is just previous to a given node. Right? Okay. So, therefore, the effort involved is to find this position that occurs just previous to a given node. Right? The way we do it is we skip through from one pointer to another pointer, one node to another node by traversing the pointers. Traversing meaning we move from one node to another node by crossing the pointer. This is just a way of visualization. And once we find the correct node, that is a node whose successor is the given position, we have found the immediate predecessor. And this is a repeated effort. Now observe that the number of pointers that we traverse is representative of the amount of time that we spend in finding the predecessor node. And therefore, if we are repeatedly querying for the predecessor node, then using the linked list data type to represent your data is a bad idea, because the algorithm will the programs that we write will repeatedly be traversing the lists from the head onwards, because in the linked list data type we have access only to the head of the list. Whenever you need to find a specific position, you have to find that position by traversing that list. Therefore, to avoid the effort of traversing the list, the doubly linked list data type is used, and it is obtained by modifying a very minor modification to the linked list data type. It is also clear that the number of traversals that we perform controls the speed of the big integer addition. That is, if more the number of pointer traversals, longer the running time of the addition algorithm. Therefore, our goal is to attempt to reduce this effort. To reduce this effort, we introduce the doubly linked list data type. Therefore, what we do is a very simple modification. At each node, we also keep a pointer to the predecessor. Therefore, we modify the node data type that we had with the linked list implementation. The way we modify it is by just adding one more pointer to the node data type, and this pointer is designed so that it will contain the address of the previous node in the list, right, or the predecessor node in the list. Therefore, the doubly linked list is obtained by extending the singly linked list in this particular fashion. Right? We essentially keep pointers to the before and after nodes for each position, right? Except for the head node of the list, or the first node of the list. The immediate predecessor is well defined, and everything else is very similar to a list. Right? All the methods are essentially similar. But since we are maintaining additional data, the implementations of some of these functions will definitely change. In particular, let us take the case of before of p. Recall that before of p was taking a position and a list as an argument, and it would return a pointer to the element which is before p in the given list. Right? Earlier, this function would essentially traverse the whole list and find the predecessor of position p, right, in the list implementation. But in the doubly linked list implementation, it is just one pointer query. That is, you only have to take the previous value. Okay? That is, you take the previous field of this particular object, right, and essentially we get the previous position to P. Other methods are conceptually the same, the return values are identical, there will be some minor implementation, minor modifications in the implementation. Right. So how do we now implement it? Therefore, here comes the second important concept. We can of course start implementing the ADT from scratch, but in this lecture we are going to do something interesting. We are going to reuse the code that is written, right, for list. When we reuse code, we have to be very careful and modify the definition of node. This is very clear. There is no conceptually the modification we have already discussed it. We will keep a pointer to the previous node. Right? Essentially, we'll have one more pointer. But when we modify the definition of the node, we should also remember to also change the name of the appropriate types, because we are working with a C programming language. So especially if you're going to use the linked list data type in the program and also the doubly linked list data type in the program, then naming conflicts must be very carefully avoided. Right? We will see that in a minute. The second modification that we need to perform is that for we need to modify the before function and other functions to take care of the fact that the node data type has one additional piece of information which ensures that we can avoid some search. Okay. Therefore, two major modifications. One, we change the structure of the node data type. We keep one additional field inside it. Second, we use this additional field to simplify the implementation of different functions. These are two conceptual modifications. Here is an implementational modification, which means that because we are going to reuse the code, right, which was written for lists, we should be very careful and ensure that the argument types and the return types of different functions are changed. The arguments in functions like size of, which are library functions, are also carefully changed. Then we also need to ensure that the names of the functions are also appropriately changed. That is, C does not provide us the feature of using the same name for a function, right, which performs the same task on different data types. We should have different function names. Right? So I repeat this, we are limited by the features of C, the programming language. So for example, if you have a function which is performed on the linked list data type and the same function is performed on the doubly linked list data type, we must ensure that the two functions have different names, especially if we are going to use the two data types in the same program. Okay? So this is another major modification that we must take care of when we reuse code. In general, whenever you reuse code, one must reuse code in a very careful manner, otherwise one may not be able to predict the kind of errors that will happen. Then we will look at a programming exercise, but for the moment let us look at our implementation of the doubly linked list data type. All right. So let us just look at the doubly linked list data type and let us see the kind of files that we are going to deal with. All right. So you will be familiar from previous lecture about the three files, list.h, listinterface.h and listmethods.h. These are the three source files, and the object file was obtained by compiling listmethods.c and it is called listmethods.o. Similarly, we create three source files for the doubly linked list. These are obtained by extending the list implementation itself. So we have three additional files now which are relevant to today's lecture. One is called dllist.h, then dllistmethods.c and dllistinterface.h. So the dllist.h contains the data type definition, that is the modified node type. The dllistmethods.c contain modifications of the list methods, right? Appropriate modifications which are carefully done. The dllistmethods.o is obtained by compiling the dllistmethods.c file. And a programmer who is programming by using the appropriate, these data types will include the DL list interface.h and the DL list and the list interface.h. So let us look at these files one at a time. As you can see, the modification is that the type name has changed. It was struct container, now it's struct D container. D stands for doubly linked list, the first letter. Then the additional pointer previous field has been added, right? And the type name has also been changed to DL underscore node from node. Right? Now it is important to note that all these type names need to be carefully changed, especially when we are planning to use both the data types in the single program. A small exercise that you should do is try using the same names, right, in C and compile, and you will see the kind of errors that happen. So then you should ask yourself, what is the right programming language for ensuring that you can use the same name to mean two different things. Just a small pointer to get you thinking. Now let's go to the DL list interface dot. So again, now we have included the DL list.h. This is the interface file. This contains methods that programmers will use. This also tells us what kinds of methods we have implemented. Okay. So let us just see if one compares the files associated with the linked list and the doubly linked list, you will find that uniformly we have changed the argument types from node to DL node. Right? Secondly, observe that we have changed all the method names. Right? Size has been changed to D size, is empty has been changed to D is empty, is first has been changed to D is first, first has been changed to D first. Observe that I have carefully added the additional character capital D to ensure that there is no confusion for the compiler because of this mistake of using the same function name, right, in two different abstract data type implementations. That is, I'm avoiding the situation where I use the same function name in two different abstract data type implementations. Especially in C, this is not permitted. So this is basically the list of all the methods that are implemented in the list methods.c, and this is what a programmer who wants to use a doubly linked list data type will include. So now let's go to the list methods.c, which contains the implementation. So this is inherited from, so this extends list methods.c. So conceptually, really nothing new happens here in terms of the different functions, right? So all the functions, for example, T size now returns the length of a list, right? D is empty. So the concept associated with each function is exactly the same. Right? The implementation details change, and the implementation details change in the following way. Let us just look at the way in which the implementation detail changes. Wherever, right? So for example, let us look at the before function. Right? So recall that the before function takes in as argument a list and a pointer and returns a pointer to the previous node of the given pointer in that particular list, in the given list. And recall that when we implemented this in the list, we had to traverse the whole list, cross multiple pointers before we get to the desired node, which is the predecessor of the given position. In this case, it is extremely simple. You just return the value of the previous field associated with the position node. Right? So therefore you take that particular node, the current node, look at the previous field, and it points to the previous node in the list, and one just returns that value. Observe that that could be null also. Right? So this is the one major change. Right? The other major change that we have is that the way we are going to, in today's lecture, we are also not just going to implement this data type, we are also going to compare the big int addition program, right, by considering two implementations. In one implementation, the numbers are stored in a singly linked list, and in the second implementation, the numbers are stored in a doubly linked list. And the way we compare the two implementations is by keeping track of the number of times pointers have been traversed while trying to perform the addition operation of the two integers. Now, we have added an additional variable, right, which keeps track of any pointer access by calling this, we have added this additional variable called dl pointer travs count. What it does, it's a doubly linked list pointer, right, and sorry, it's a variable that is called pointer traversals count, and it's pointer traversals count in the doubly linked list implementation. Right? It's a variable which is global to this particular module, right? Which means in any function it can be changed, right? And we have initialized it to 0. Okay? So let us see where all we change it. Every time a pointer is being traversed, we increment this variable to recognize the fact that a pointer has been traversed. Right? So where are all the places where the pointers get traversed? Recall that when you want to compute the size of the list, then you have to essentially so when you keep track of the size of the list, you essentially have to traverse a pointer to go from one node to another node, right? And therefore we are incrementing the value of the count. Another place is when we have to find the last element in the doubly linked list. We traverse the whole list, right? We skip pointer after pointer, and every time the pointer is skipped, we actually we increment the counter. Right? These are the only two places where this counter is changed. Let us just look at the list. Methods.c. Here also we do the same thing. So we have introduced a new counter called L underscore pointer underscore travs. This counter keeps track of the number of pointer traversals in the linked list method, right? In the linked list implementation. Again, this is a global variable, global to this module, which means it can be modified in any function inside this particular file. So again, when you want to find the last element of the list, we skip the pointers one after the other, and then the pointer travs count is incremented. And another place is here, it's very important. When you want to find the predecessor of a given node, again you have to skip the pointer starting from the head of the list right up to the point when we find the appropriate node that we want. So again here, the pointer traversals count is incremented, and therefore these are the two places at which the pointer traversals count is incremented in the list implementation. Therefore we have modified the list implementation in a small way by adding one counter which is global to that particular list implementation, right? And this counter, basically the value is incremented whenever the pointer traversal instruction is executed, just after it or just before it. So these are the only changes that we have made, right? And observe that we have taken the list implementation, made a copy of it, and then modified it by just updating the appropriate arguments very carefully, right, for all the methods. But you would have also observed that we changed the function names carefully. So this completes the implementation of the doubly linked list abstract data type. Right? I'm not going to compile the doubly linked list abstract data type implementation because subsequently I have added additional methods which are relevant for the next lecture. For example, I've introduced some functions called midpoint, comes after, and binary search, and so on. Right? These are not compiled yet, so therefore I'm not going to compile it and show it to you. Right? However, you can see that I have already compiled the doubly linked list implementation quite recently, right? And it is available for me to use in the programming exercise that we have planned. So now let's go to our programming exercise. And before that, so observe that so far we have completed the definition of the doubly linked list abstract data type, which is a very important thing. We also found the motivation for why we want to come up with a new data type. Right? So essentially we want to gain some efficiency. And then we saw that we can reuse code that has already been written. For example, whatever code we have written for the list abstract data type, we reused it for the doubly linked list abstract data type, and we carefully modified it. Conceptually, they were not major modifications because essentially both are lists. You only have to keep track of, pointers carefully. You need to ensure that the previous field in the doubly linked list nodes are appropriately set, and so on and so forth. So therefore, the modifications were very simple. We just made a copy of the linked list methods.c and changed the data type names at all the arguments. The return values were changed. The function definitions were appropriately changed, and care was taken to ensure that the values of the previous field in each node was meaningfully set. Right? So I encourage you to look at the code. We will make the code available to you on Google Drive as a PDF, and you can take a look at it. So now let's go to a short description of the programming exercise, which is a comparison between the efficiency of the doubly linked list based implementation and the linked list based implementation of adding two large integers. Right? So that is the focus now. Right? So let us just go to the description of the exercise, which is in the PowerPoint slides. Right. Question is the same. One has to perform big number addition. Right? But the goal is to compare two implementations of big number addition. The first implementation is based on the list data type, and the second implementation is based on the doubly linked list data type. Our implementation of this programming exercise will print out the answer. It will also print out how many times the pointers were accessed by both the methods. Right? And in a subsequent lecture, we will also show you how much additional space has been used by the doubly linked list data type. Therefore, you will understand the trade-off between using more space to gain some more efficiency in terms of time. So now let us go to the implementation of this performance monitor program. Right. So the performance monitor program is called perfdll.c. Right? It is an application program which uses both the data types, which means that if you look at the C code, you are going to see that both the data types, both the header files have been included, and the program uses methods associated with both the data types. Right? And C does not permit you to have same function names, right? And therefore we have also ensured that functions which perform similar operations have different names in the implementations of the abstract data type. Before we look at the code associated with the abstract data type, let us just take a look at one or a few runs of the abstract data type. So let us compile it first. Right. So let us just look at it. GCC, the compiler, you compile this particular program. The output goes into this executable perfdll, and you link the object files link method.o and the doubly linked list methods.o. Now the executable is ready. Let us run it. So let me give some really large number which you can verify immediately will not be cannot be stored in any variable of the data types provided by the C programming language. All right. So let us just see this. These are the two numbers. It is very easy for you to verify that the sum, which is in the fourth line, is correct, right? But prior to the fourth line, that is in the third line, observe that I have printed out, right, or the program has printed out the number of pointer traversals with a linked list implementation. That is, when the two numbers were stored in two separate linked lists and added, the number of pointer traversals was 8,374. But when you use a doubly linked list, the number of pointers is about 60%, right, or a little more than 60% of the number of pointer traversals, when 60% less than the number of pointer traversals made when you use a linked list. Okay, let me say this again correctly. Okay. So the number of pointer traversals made when you use a doubly linked list is only 60% of the number of traversals made when you perform the implementation with a doubly linked list. Let's look at even smaller numbers. This can of course sit in an appropriate integer variable, but we are not worried about it. But again, you can see that it's close to like 67-68%. Right? The number of pointer traversals made with linked list is 102, and the number of pointer traversals made by doubly linked list is about 72. Let's try even smaller numbers. Right? And as you can see now, it's almost 80% of the total number of pointers that the doubly linked list uses at most 80%, right, of the number of pointer traversals as used by a linked list implementation. Let's do this for 2 just to see. All right. So this is interesting. Observe that observe the number of pointer traversals in both the implementations is the same. Therefore, as the size of the numbers keeps reducing, observe that the implementation with linked list and doubly linked list seems to be more or less the same. I mean, it's getting close. As the numbers reduce, it reduces from 65% onwards to something like 68% to 80% to 100%. That is, they use exactly the same number of pointer traversals. And observe that this is an experimental validation of our quantitative analysis of quantitative effort. Right? So recall that, experimental validation of our analysis of the qualitative effort. Right? So recall that we started this discussion by saying how much effort is put into traversing pointers, and we did not assign values to it. But here is an experimental validation. We are essentially saying that it looks like the doubly linked list implementation uses only about 60% of the number of pointer traversals made by the singly linked list implementation. And it is not clear, right, what the exact percentages from the analysis, and that is typically what is the content of a formal analysis. Like if you study a data structures and algorithms course, such concepts are carefully analyzed, right, in a course. But in this course, we are focusing more on the experimental evaluation. So let's try even a larger number to see what the percentage looks like. Alright, so it almost looks like 60%. As you can see, the number of pointer traversals made with the linked list implementation is about 30,000. On the other hand, with the doubly linked list, it is 20,000. Right? So it is about 66%. Right? That seems to be the right number. I leave that as an exercise for you to exactly quantify by looking at the implementation. What is the percentage relationship between the number of pointer traversals? Now let us go to the program itself, the source file. Okay, as you can see, we have included both the list interface and doubly linked list interface.h. Observe that the two variables which are the counters, okay, which keep track of the number of pointer traversals and are defined to be extern variables here. This means that the compiler uses this declaration, right, in the compilation process. And observe that the variables are not initialized here. The variables are initialized in the appropriate modules. Right? Similarly, both these variables are defined as extern. Right? Extern is a keyword which basically tells the compiler that this variable is defined elsewhere, right? Or this data item is defined elsewhere. And most likely, the good programming practice is to ensure that the modification of this data item is also done elsewhere. Right? I repeat this: the two counters, right? We are using the two counters which are present in the list methods and the doubly linked list methods .c files, right? And they are included here, right, with the extern keyword, and this is mainly for the compiler to go ahead with the compilation. The function prototypes are essentially unchanged. Right? The check value character, which checks whether the character is a meaningful character, that is, we only want to deal with numbers, characters which correspond to digits. Right? That function doesn't change. We have re-implemented the print list function, right? And we called it the dprint list function. And the only change is the data type as the argument has changed. And the code inside this function also is modified to reflect it. Let us just take a look at it. Okay, so if you look at the dprint list implementation, the argument is changed, right? And otherwise, really nothing much has changed. Essentially, we are reusing the code fairly efficiently. Right? Similarly, the dadd method, conceptually, where we are adding the two lists, right? In this case, the numbers are stored in two doubly linked lists. The dadd method is to add the two doubly linked lists, or add the two numbers in the two doubly linked lists. Let's just go to the particular code. The name of the function has been carefully changed, right, because of the limitations of the C programming language. So let us just look at the implementation of dadd. Really, it's exactly the same implementation as the add function itself, except that significant care has been taken to ensure that the pointers are all appropriately set. For example, whenever a new node of the DL node type is allocated, both the next pointer and the previous pointer are set to null. Similarly, if you look at this piece of code, when a node is inserted into the list, that is, when one more number is inserted into the list, that becomes the head of the list. The previous head of the list now points to the new node that has been created. This is another thing that has been implemented very carefully. Otherwise, conceptually, the addition algorithm really does not change. Right? The other things that have changed is that whenever we needed to use the before function, right, in the list implementation, it's been changed to the d before, right, and so on and so forth. Therefore, the code is just being changed by ensuring that the methods associated with the doubly linked list implementation are used. What these methods actually do, there is no major conceptual change. So now let us look. Therefore, we've convinced ourselves that the methods haven't drastically changed. The implementation algorithms are just the same, and it's just a careful reuse of code. Careful in the sense that the names of the arguments have been changed, the names of the functions have been changed, and wherever the previous pointers have to be set carefully in the doubly linked list methods, we have done that also very carefully. These are the only changes. Algorithmically, there is no change between the add method or the print list method in either the list implementation or the doubly linked list implementation of this program. Okay, so let us just look at the top level structure of this program, the flow chart, so to speak. Okay, so the first number is read into number 1, right, which is a linked list. The same number is read into D number 1, which is a doubly linked list, the first node of the doubly linked list. Then the numRead function is called, and the numRead function has been modified. It takes 2 arguments. One is a pointer to the first number, which is a list, singly linked list, and it takes a pointer to the doubly linked list, which is supposed to contain the same number. On returning from this function call, the pointer number 1 contains the first number, and the pointer D number 1 contains the same first number, except that in the D number 1 pointer points to a doubly linked list, and the number 1 pointer points to a singly linked list. Same with number 2. Conceptually, there is nothing, right? We now have 2 lists, right? 2 sets of lists. One set for number 1 and number 2. These are singly linked lists. The other set for D number 1 and D number 2, which are doubly linked lists. Okay, now we calculate the result using the 2 functions, which is add and deadd. Note that deadd takes as arguments 2 doubly linked lists, and add takes as the arguments 2 singly linked lists. Now what we do is we print the number of pointer traversals, which is the counter variable which is associated with the list methods.c. Then we print the result. Then we print the total number of pointer traversals made by the doubly linked list implementation, and then we print the result. The more interesting thing for you to note is that observe that the counters are not modified in this particular program. The program has been carefully designed so that the counters are modified only in the appropriate modules. This is a good programming practice, right? So whenever you use a certain module, you ensure that the module is designed very carefully to ensure that all the necessary data items associated with the module are modified only by the module and not by any other calling function. So this completes the implementation of the doubly linked list data type, right, and the performance analysis of the linked list implementation and the doubly linked list implementation, and a comparison between the two of them. This more or less completes the lecture now. Okay. So observe what we've done so far. We defined the abstract data type doubly linked list. We argued about its importance and why it is important. Right? We came up with a qualitative reasoning as to why we need the doubly linked list data type. Then we went about and implemented the doubly linked list data type by reusing code from the list data type, and we made the modifications very carefully. Right? And then we tested the implementation by making a performance analysis program which implements the big number addition in 2 ways. The first implementation stores the given numbers in a singly linked list, adds them, and the second implementation stores the given 2 numbers in the doubly linked list and adds them. And we calculated, our program actually kept track of the number of pointer traversals and printed them out. That way we got a scientific method of comparing the 2 implementations. I mean scientific because we do not do a formal proof, we only do an experimental validation. What we concluded experimentally is that the doubly linked list implementation traverses a lesser number of pointers than a singly linked list implementation, and it looks like that it traverses only a 60% of the number of pointer traversals made by a singly linked list implementation. This is a very interesting fact, right? And this also shows that a doubly linked list implementation is very useful for such arithmetic purposes for large numbers. However, we did not measure how much space, additional space was used. This we will definitely do in the next set of lectures this week itself. So what are we planning to do in the next week? The plan for the next week is that we will talk about the array abstract data type very quickly. We will not go into the array abstract data type implementation because the C programming language provides us features for manipulating and accessing arrays. What we will do is we will use the array associated with the C programming language. We will use our doubly linked list implementation, and we will come up with a performance monitor for the binary search algorithm. We will count very carefully a certain interesting parameter which will tell us which of the two implementations is more efficient. Is it binary search on an array, or is it binary search on a doubly linked list? Again, it will only be an experimental validation and not a validation by a formal proof or a mathematical counting argument. After that, we will quickly describe the stack and queue abstract data type in this week's lectures, and next week we will apply the stack and queue abstract data types to solve certain interesting problems. So that brings to end today's lecture. So I have some requests from my side and the TA's side to all of you who are attending this course. Right? We appreciate the interaction on the forums, and we are happy to trigger such an interaction, but many of your questions requesting for extra time cannot be really honored. We've already given extra time for the first programming exercise, so I would encourage you to take your time and do the programming exercises and not request for additional time if you're not able to finish it within the given time. We may probably give you approximately 2 or 3 days extra for every assignment, right? But we cannot give you a large amount of time because the course itself runs only for about 2 months, right? And we cannot give you an inordinate amount of time. We have to move on to the next assignment. But I do appreciate your concern that you also want to learn from the material and participate in the certification exam. I appreciate that. My advice to you on that matter is that you could probably do the course now and become stronger programmers, do the programming assignments yourself, right? Work through the details, take your own time, and appear for the certification exam at a later date. This is something that that I could suggest, right? As one of the approaches to ensure that you get the best out of this course. And as you will see that the second assignment has been released, and we will ensure that the programs that I am using to explain different concepts to you in these lectures are available to you in appropriate documents for you to read through them and use them. So thank you very much, and we will be uploading this lecture shortly, and the next 2 lectures will follow shortly. That brings to the end today's lecture.